Okay, in section 1.3, we'll be looking at implications, and this is also covered in Zybook's section 1.4. So implications are actually another logical connective. So if you think about it, we've already considered a few different logical connectives. We've done the negation, the conjunction, the disjunction, and the exclusive or. So we've already looked at those ones. This is another way to create compound statements, and implications are actually the most important to us. Implications are statements that are like this: if P, something that is true or false, then Q, something else that's true or false. So if one statement, then another statement. And the reason these are so important is because all theorems are expressed that way. Okay, so I often tell my geometry class, I'll ask them, what's the Pythagorean theorem? And they'll want to say a squared plus b squared equals c squared. Well, that's not quite right. The Pythagorean theorem is actually if you have a right triangle with legs of length a and b and a hypotenuse of length c, then a squared plus b squared equals c squared. Right? It's an if-then statement. If you just say a squared plus b squared equals c squared, it sounds like that's true for every single a, b, and c in the entire universe. It's not true. It's only under certain conditions, only if those happen to be the legs and hypotenuse of a right triangle. Okay, so because theorems are expressed as implications, we'll be particularly concerned with these implications in this course. Okay, so the notation for an implication is P and then this arrow, this double arrow, Q. Okay, and stated in words, it would be if P, then Q. At least that's one way to state it in words. Okay, we also sometimes call an implication a conditional statement. So if you see the term conditional statement, it means the same thing as implication. And then when you look at the two statements that are in this compound statement, we have special names for the two statements. So the P, the thing that comes before the arrow, that is called the hypothesis. Okay, so this hypothesis, then, and then the Q, the things that comes after the arrow, is the conclusion. So if hypothesis, then conclusion. So let's look at the truth table for the implication. Okay, so I'm just going to go ahead and fill in our P and Q values here. So Q is going to be true, false, and P is going to be true, true, false, false. Okay, and then we'll put the logical implication over here. Okay, and then we have this statement here, the truth value of the implication statement. It's only false when the hypothesis is true and the conclusion is false. So if we look here, the hypothesis is true, that would be here or here, and the conclusion is false. Q is the conclusion. So this is the only place where we have a true hypothesis and a false conclusion. So this is the spot we're looking at. That's the only place where the implication is false. So this one is false and all the others are true. So that will be our truth table. Okay, so that, as an if-then, okay, so we would say true, if true, then true is true, if true, then false is false, if false, then true is true, if false, then false is true. Excuse me. That might not be completely intuitive to you, but I have in a couple of slides we'll look at a particular example with a real world kind of example, and hopefully these assignments of truth values will be a little bit more intuitive when we look at a specific example. So just sit on that for a minute and we'll get there in a second. Okay, so of course we often have the job of taking things that are written in English words and turning them into a logical kind of statement. And so there's a variety of ways that these English sentences or English words can show up and translate into the statement P, then Q. Okay, so the most obvious one is just if P, then Q. Okay, so that's one way that could get translated. We also have Q if P. Okay, so really it's just kind of a way of rewriting this. You know, if P, we've just omitted the word, then Q. So Q, if P. It's kind of just the same thing there, just in reverse order. Okay, we can also, this is in logical implication, so we can use the word implies. So P implies Q. And this one is a little tricky because it looks almost like this one, but there's an extra word, only if. Okay, so P only if Q. And notice the difference between the use of if by itself and only if. So if the if is by itself, the conclusion is first, and then the hypothesis is whatever comes after the word if. If we have only if, the conclusion comes after the only if. Okay, so notice the distinction between those two. Those can easily get mixed up. We want to make sure, like here, the conclusion comes first, then the hypothesis. When the only if, the hypothesis is first, conclusion is next. Okay, then we have P is sufficient for Q. And the other tricky one is another one where the conclusion comes first, so Q is necessary for P. So every single one of these is translated P implies Q, or if P then Q. So these are all different ways of saying exactly the same thing. So if that's not completely intuitive to you, once again we're going to look at a specific example so that can help us kind of reason that these are all actually saying the same thing. So suppose we have a student named Susie that took discrete math last semester. Okay, so if Susie obtained all A's last semester, so imagine she took some other classes too. She took chemistry and history class and you know, English class or whatever. She got all A's last semester. Then Susie received an A in discrete math. Okay, so pretty clearly that would be true. If she got all A's, okay, then she would have had to have gotten an A in discrete math because that was one of her classes. Okay, so this would be a true logical implication. Okay, so let's look at another way that we might say this. Okay, so first let's look at this. So here, if, and then this, Susie obtained all A's last semester, that is our hypothesis, or our, you know, like our P. Okay, and then Susie received an A in discrete math. This is our conclusion. It's like our Q. Okay, so this is definitely P implies Q. Okay, so we could say Susie received an A in discrete math if she obtained all A's last semester. Okay, so certainly Susie received an A in discrete math if we know that she obtained all A's. One of those A's certainly had to be in discrete math. Okay, so let's look at how this is arranged. So Susie received an A in discrete math. Well, that's this part right here. So that's a Q. So this is our Q. So we have Q if she obtained all A's last semester. Well, that's here, all A's last semester. That's P. So this is our P. So notice this is in the form here, Q if P. Okay. It's logically the same as this one. So this would still be interpreted as P then Q. Okay, so it's the same as this. Let's look at the next one. Susie obtaining all A's last semester implies that she received an A in discrete math. Okay, so it does. It implies she got all A's, so that implies that she got one in math as well. Okay, so let's look here. Obtaining all A's. Okay, obtaining all A's that's the hypothesis of this first part is P. And then we have implies received an A in discrete math. That's our Q. Okay, so P implies Q. That's like this second one. Okay. Susie obtained all A's last semester only if she received an A in discrete math, right? So this could only happen if she also had gotten an A in discrete math. If that hadn't happened, of course, this couldn't happen, right? So she can only get this if she receives an A in discrete math. Okay, so obtaining all A's last semester, that's P. and then she received an A in discrete math. That's our Q. And then we have this only if in the middle. Okay, so that's this one, P only if Q. Susie obtained all A's last semester is sufficient for receiving an A in discrete math, right? If she got A's in all of her classes, that would be sufficient for us to know that she received an A in that one particular class, discrete math. Okay, so all A's last semester, that's our P. And then we have is sufficient for, and then the A in discrete math, that's this one, that's our Q. So this is just like P is sufficient for Q. And then our last one here, receiving an A in discrete math would be necessary for Susie to have obtained all A's last semester, right? This would be absolutely necessary. If she didn't get an A here, for all A's to happen. Okay, so here we have the A in discrete math, that's the Q. So here the Q comes first, that's necessary for, and then the all A's last semester, that's the P. Okay, so this one is our Q is necessary for P. So these all give us the same information. They're all written this way. It's just the orders are different. The ones that you really need to be careful are this P if, or Q if P, and the Q is necessary for P. So those are the only two where the conclusion comes first in the sentence and the hypothesis comes last. So those are a little bit tricky. You got to look for those ones and make sure that you recognize which is the hypothesis and which is the conclusion. Okay, so remember we had this table and I said it might not be intuitive, but we'll look at an example. So this is that example that I promised. Okay, so suppose I make this statement. If it's Tuesday, then my daughter has dance class. And we want to consider, like, under what conditions would I be making a false statement, or under what conditions would I be telling a lie when I said that. Okay, so imagine it's Tuesday and my daughter has Tuesday, then my daughter has dance class. It is Tuesday and she has dance class. So I told the truth. So this would be a true value. Okay, let's suppose it's Tuesday but my daughter doesn't have dance class. Well, I said if it was a Tuesday, then she would have dance class. It's a Tuesday, she doesn't have dance class. So I lied. Okay, I made a false statement. That is false. Okay. Now let's say it's Thursday. It's not Tuesday. So notice here my hypothesis about it being Tuesday is false. Okay, I've got a false hypothesis. And my daughter has dance class. So it's Thursday and, oops, this is supposed to say my daughter has dance class. So, was I lying? Well, no. This isn't a false statement. I said if it was Tuesday, my daughter had dance class. I didn't really make any claim about what happened when it wasn't Tuesday. When it was Thursday or Wednesday or Friday, I didn't make any claim about this. So, it's Thursday and my daughter has dance class. I was still telling the truth about Tuesday, right? And so, this is still a true statement. Let's say it's Wednesday and my daughter doesn't have dance class. So I have got a false hypothesis because it's not Tuesday, it's Wednesday. I've also got a false conclusion because my daughter doesn't have dance class. Okay, but did I tell a lie up here? No, I didn't tell a lie. It's still a true statement. Okay, it's just that this doesn't really apply, right? So this is still a true statement that I made. So this statement up here, the only conditions under which I would be lying is if the hypothesis was true, but the conclusion was false. This is the only time I'm making a false statement. So this is a little bit tricky, but notice, like, for when we have this false hypothesis, and basically the statement doesn't claim anything about when the hypothesis is false. It's only making a claim about what happens when the hypothesis is true. So when you start out with a faulty hypothesis, you can prove anything. You can get false or true. It doesn't matter. So if you have a false hypothesis, you're always going to have that true implication. Okay, so let's look now at an example. So we've got a real number x, and we have some open sentences. So p of x is x squared equals x, and q of x is x plus 1 squared equals 0. Okay, so we want to express the implication in words. So let's go back to this page back here. Let's maybe pick one of the tricky ones where, like Q if P, where the conclusion comes first and then the hypothesis. Okay, so let's do this as Q if P. So our Q is x plus 1 squared equals 0. And then if, and then our P is x squared equals x. So that's one way we could write it. Okay, let's do this. P is sufficient for Q. So let's do that. So P, that would be x squared equals x, is sufficient for, and then our Q, x plus 1 squared equals 0. Okay, so these two statements are saying exactly the same thing. They're both saying this. P, if P then Q, or P implies Q. Okay, now let's look at some examples where we could get this implication to be true and where we could get this implication to be false by, okay, fixing or assigning an actual value to A. So in order to do that, we want to figure out all the places where P of A or P of X could be true and all the places where Q of X could be true. So let's first consider P of X. So here's our P of X, that's x squared equals x. Okay, so where could that be true? Well, we should subtract x from both sides and then factor. We would get x times x minus 1 is 0. So the two places where this could be true is where x is equal to 0 and where x is equal to 1. And then for Q of x, okay, that one is x plus 1 squared equals 0. And the only place that is true is when x is negative 1. So that's the only value. Okay, so we want to give an example for a value A. Okay, so that if we put A into the open sentence P, okay, and into the open sentence Q, that will have P implies Q, P of A implies Q of A is true. So if you think about this, this could happen like if both of these were true, right? So if we had a true hypothesis and a true conclusion. So is there an A that can give us a true hypothesis and a true conclusion? Okay, well, if I put in 0, the hypothesis would be true, but the conclusion wouldn't. If I put in 1, the hypothesis would be true, but the conclusion wouldn't. So I'm not going to be able to find a true implies true. Okay, the other way to get true besides this one is to have a false conclusion, and then anything can happen. So here, I can choose a value, okay, that would make the hypothesis false. So I just have to choose a value that's not 0 and not 1, because those make the hypothesis true. Anything else will make the hypothesis false. So for example, we could choose our A to be negative 1. Okay. In that case, if we did P of negative 1 implies Q of negative 1, well, when we put negative 1 into our P, negative 1 squared equals negative 1, that's false. And then when we put it into our Q, negative 1 plus 1 squared equals 0, that's true. And then false implies true is true. So it does indeed make a true value. Okay. We could have picked anything else too. We also could have picked like x equals 2, and then we would have had a false implies false, but that's still true. So that would have worked as well. Okay, let's look at the next one. This time we want a value B, so that when we put B in, we're going to get a implication that's false. Now there's only one way to get a false, right? That's with a true hypothesis and a false conclusion. So we need a true hypothesis and we need a false conclusion here. Okay, so to get the hypothesis to be true, we have two choices, 0 or 1. Unfortunately, either one of those would make the conclusion false. So we'll just pick one. Let's say we'll do B equals 0. Okay, so if we put that in there and 0 in there. So if I put 0 into my P function, will that be true? Yes. And if I put 0 in here, that one will be false. A true hypothesis and false conclusion, so true implies false, is false. So we made it a false statement. Okay. All right. So let's do a few more examples. So we want to determine with each of these following statements is true or false. Okay, so once again, it's good to have your little sheet handy. Okay, so here we've got some kind of statement. Okay, and then an only if, and then another statement. So here on the only if, the P, the hypothesis, comes first. So this part is our hypothesis. So this is going to be our P. And then after the only if is the conclusion. So this is our conclusion. So this is our Q. Okay. So we're going to have P implies Q like this direction. All right. So 0 is negative. That is a false statement. 0 is unsigned, so we get false there. And then the conclusion, -1 is negative. Clearly, that's why it's called -1. So this is true. A false implies true is true. Remember, with a false conclusion, you always get true. Okay, so that one is true. Going on to B. We have is sufficient for. So let's look at our little sheet here. So is sufficient for, okay, the P is, the hypothesis is going to come first, and the conclusion will come second. Okay, so this is going to be our hypothesis. So that's our P. And this is our conclusion. Okay, so this is our Q. So this time, our hypothesis, the absolute value of 3 equals -3, that's false. And then our conclusion, the absolute value of -3 equals 3, that one's true. And false implies true, just like before, this one is true. And let's look at the last ones. We have the words is necessary for. Is necessary for. This is one of the tricky ones. This is one where the conclusion comes first. So this is the conclusion. So this is our Q. Okay, and then the P value comes second. So that's our hypothesis. This is our hypothesis. So that's our P value. Okay, so we'll evaluate the hypothesis first. Okay, so -1 cubed equals -1. That's true. And then the conclusion is that -1 squared is -1. That's false, because a negative times a negative is a positive, right? That should be a positive one. This is false. And true implies false is false. That's the only time we get a false statement, is if we have a true hypothesis and false conclusion. Okay. All right, now some other statements that are closely related to the implication are things called the converse, inverse, and contrapositive. So they're related in that they use the same statements, the component statements, the P and the Q, but we put them together in different ways with the implication. So if we change the order and we make this is our original statement, we make that hypothesis into the conclusion, and we make the conclusion into the hypothesis to make a new statement, that's called the converse. So we just swap the hypothesis and the conclusion. That's the converse. Okay. From the original statement, if we negate the hypothesis and negate the conclusion, but keep them in the same order, that one's called the inverse. And then if we swap and negate, so notice we swap the order and we negate them. Okay, that is called the contrapositive. Okay, so we have special names for just rearranging those statements and implications and putting negations with them. Okay, so a nice thing to hang on to and to know is that the contrapositive and an implication are logically equivalent. Okay, so that means, so the original statement, that's P implies Q. Okay, that is logically equivalent to the contrapositive, so this one, not Q implies not P. All right, so let's do truth tables for those statements and convince ourselves that indeed they are logically equivalent. So for the Q's, we're going to do true, false, true, false. And over here, the true, false, true, false. And for the P's, we're going to do true, true, false, false. True, true, false, false. Okay, let's do the original statement first. So true implies true is true. True implies false. That's the only one that's false, right? A true hypothesis, false conclusion. And when we have a false hypothesis, anything goes. We always get a true statement. Okay, so that are the truth values there. Okay, so for this one, let's first negate Q. So we're going to get false, true, and negate P. We're going to get false, false, true, true. And now we want to look at these two, the negated values, and use those in our implication. So we have false implies false. That's true. True implies false. That's the false one. False implies true. As long as you have a false hypothesis, you always get true. And then true implies true is true. So this is the final truth value for the contrapositive. So notice they match everywhere. Since they match, they're logically equivalent. Okay. So that is the original implication and the contrapositive. So that's what we've showed here, that they're logically equivalent. Now it's also true that the converse and the inverse are logically equivalent. So let's also look at this. Q implies P. That is the converse. And then the inverse, this not P, implies not Q. So not P implies not Q. So let's look at the truth value of those and prove that those are also logically equivalent. Okay, so just like before, our Q is true, false, true, false. Just go ahead and fill those in, and then our P is true, true, false, false. Okay, I'm just going to copy the not P's from here. So that's a false, and a false, and a true, and a true. And I'm going to copy the not Q's from here. So this is going to be a false, and a true, and a false, and a true. That will just save me a little bit of work in my table. Okay, and now I need to do the implication. So true implies true is true. False implies true is false. True, sorry, is true. False implies true is true. True implies false is false. I was getting ahead of myself. And false implies false is true. So notice anywhere where we have a false hypothesis, we should have a true value for the implication. Okay. And then over here we have a false implies false is true. False implies true is true. True implies false, that's our only false one. And true implies true is true. So these are the two final values that we should be comparing. Notice they're exactly the same. True, true, false, true. And notice that they're not the same as these ones. So they're not logically equivalent to either of these, but they are logically equivalent to each other. So the inverse, the converse and the inverse are logically equivalent. Okay. And this is going to come up later when we start studying proofs. One thing that we'll find is like we said, theorems are often written as if-then statements. And one thing we'll see is sometimes it's easier to rewrite something as its contrapositive and prove it that way. And we'll call that proof by contrapositive. And if you prove the contrapositive is true, that's equivalent to proving that the original statement is true because they are logically equivalent. So we can use P implies Q and not Q implies not P interchangeably because they're exactly the same in terms of their logical values. Okay. So our next example, we want to state in words this implication P of x implies Q of x. Also state its converse, its inverse, and its contrapositive. And then we're going to look at each of those and determine the truth value of those statements. Okay, so first let's do the original statement. Okay, so our original statement is P of x implies Q of x. So our P of x is x equals -2, or so I'll just put if x equals -2, then, and then our Q of x is absolute value of x equals 2. Okay, that would be the original statement. Then let's look at the converse. So the converse, we're going to swap the order, right? We're going to put the Q first and then the P. So the Q, that would be absolute value of x equals 2. So if that, then, and then our P, x equals -2. That would be the converse. Then let's look at the inverse. So the inverse, we do not P. So that would be if, and then not x equals -2, or x is not equal to -2. Then not Q. So not Q is the absolute value of x is not equal to 2. And finally, we want to look. Okay, so this one starts out if, and then we swap and negate here. So if not Q, so if absolute value of x is not equal to 2, then not P. So x is not equal to -2. All right, so those are the different statements, and now we want to determine the truth values. Okay, so suppose that x is indeed -2. Then what are the possible truth values for the conclusion? Well, x is only one value, so you could only substitute one value in there, and the absolute value of -2 is indeed 2. So when this would be true, you'd have to get this as true, and you get true implies true. So this one has to be true. How about the converse? Okay, if the absolute value of x equals 2, there's two possibilities. Okay, either x could be 2 or x could be -2. So the question we have is, could I find a situation in which I had a false hypothesis? So a false hypothesis, sorry, could I find a situation where I have a true hypothesis but a false conclusion? Okay, so if I can ever find a case like that, then this in general, I can't claim that this is a always true statement. Okay, I could maybe say under certain situations it might be true, but I can't say it's always true if I can find even one counterexample or one case where it's not true. Okay, so there were two choices here. So when x equals 2, okay, my hypothesis will be true. And then x equals -2. Well, 2 doesn't equal -2, so my conclusion is false. Okay, we know that true implies false is false. So this one, since I can find a case where it's false, it's not always true, it's a false statement. I can't claim that that will always happen. Okay, now let's look at the inverse. If x is not equal to -2, so I can pick any number besides -2. I can pick -3, I can pick -1, I can also pick positive numbers like 2 or 7. Okay, if I picked any of those numbers, okay, I would still have a true hypothesis. Would one of those also give me a false conclusion? Well, yes. So again, when x equals 2, okay, 2 is not -2, so my hypothesis is true. But the absolute value of 2 is equal to 2, so my conclusion would be false. True implies false is false, so this one is also false. And it's a good thing that we found it's false because we know the converse and inverse are logically equivalent. So these better match, right? If these didn't match, okay, we would be in trouble because these are logically equivalent. They have to have the same value. Okay, when we think about that, the contrapositive, we already said that that is logically equivalent to the original. So we know we're going to get true, but let's convince ourselves that we would get true. Okay, so here, if we pick some number, now the absolute value can't be 2. So we can't pick 2, and we can't pick -2 to make this one true. So if we have any numbers, then they're not 2, and they're not -2, then this one will also be true. Okay, so anytime that this one is true, we have to get this one as true as well. If this one were false, that one would also be false. All right, so there's no way that we can ever get a true hypothesis and a false conclusion. If this hypothesis is true, this one has to be true as well. So this will give us a true statement, which it should because it's logically equivalent to the original. So these two should match just like we have found they do. Okay. Okay, so we just have shown that the implication is logically equivalent to its contrapositive. Okay, we have other expressions, okay, for P implies Q that are logically equivalent to as well, and some of them don't involve implication like this one. Okay, in particular, we have this implication law called also sometimes called conditional identity. Okay, that is equivalent to not P or Q, so not the hypothesis or the conclusion. So these two things always have the same truth value. So let's go ahead and verify that using a truth table. So we'll do P implies Q, and we'll compare that to the not P or Q. Okay. So let's do, we've got our true, false, and the true, false. I'll go ahead and fill those in for P and Q over here as well. Okay, and let's look at the implication. So true implies true is true. True implies false is false. False implies anything is true. Okay, so we've got those final values for the implication. The not has the highest precedence, so we have to do the not first. So this will become false, false, true, true. And then the two things that we will be ORing together are these right here. So we'll do false or true is true. False or false is false. True or true is true. True or false is true. So those would be the values here. And so notice, true, false, true, true, they match exactly. So since these match, they are logically equivalent. Okay. So we can use them interchangeably. Whenever we see this, we could replace it with that. Whenever we see that, we could replace it with that. Okay. So let's look at another theorem. So if I had not and then P implies Q, so the negation of an implication, that would be equivalent, logically equivalent to P and not Q. Okay, so remember last time we talked about using some laws of implication rather than truth tables for proofs, and that is kind of a handy thing to do here. Sometimes it's a little bit shorter and less tedious, so let's try that here. So we look at the left-hand side of the logical equivalence and see if we can substitute logically equivalent statements and eventually derive this P and not Q. Okay, and so this part of it, P implies Q, I know that's logically equivalent to not P or Q. So I could replace what's in parentheses with this not P or Q. And we can do that because of this implication law. So the implication law says those are logically equivalent. I can replace one with the other and they're still exactly the same thing. And now, if you look at this, this looks like something we've seen before. So this is a application of De Morgan's law. So you can kind of sort of distribute this negation through, and then change the operation in the middle. So this turns into not P, and then this and this or changes into and then not Q. So this is by De Morgan's law. And now it almost looks like we won't. We have the and, we have the not Q. We just need to replace the not P with P. Okay, and not P is logically equivalent to P. So we can replace that, and that is the double negation law. Okay, and so that is a proof that what we started with up here is logically equivalent to the value that we have at the end, and maybe just a little less tedious than doing some truth tables. I kind of like these. They're fun. Okay, so let's practice using our laws of logic and see if we can do these other ones. So let's start here with A. So we've got P or Q, and we want to show that that is logically equivalent to not P implies Q. Okay. So when you look at this, you might look at, try to make a comparison between one side and the other side and see, what could I do to get from this side to that side. So one thing that I notice here is that this P has a negation in front of it, and this P does not have a negation in front of it. So how could I introduce a negation? Well, if I want to add some negations, I could use the double negation law and replace this P with not P. Okay, so that would be a good place to start. So that would be by double negation. Okay. And now if I look at this, and sometimes you have to kind of work backwards and see how this is going to work. But this, so if you think about it, like if I were to use the implication law on this, so the implication law here, yeah, so the implication law says if I have something implies something, so I have, something here implies something else, I take not the first thing. So if I were, that would be like not the first thing, which is not P, or, and then the second thing. Okay, so if I were to apply the implication law to this, it would turn into this. Well, that's exactly what I have here, right? And so this right here is logically equivalent to this not P implies Q using the implication law. It's a little bit easier to see sort of backwards applying the implication law here rather than trying to extract the implication from that. Okay, let's look at the next one. So we have P and Q, and we want to show that's logically equivalent to not, and then P implies not Q. Okay, now this one's a little bit tricky. Once again, you might want to kind of think about working backwards. Okay, this one doesn't have any implication in it, and this one does. So let's say if I kind of wanted to get rid of the implication, if I use the implication law, it's not, so I'm going to leave this out here. And I would have not the first thing or the second thing. Okay. So applying an implication law to this would turn it into this. So if I look at that, okay, like if I could get to there, then I could just use the implication law to get back to here. So this is kind of our like cheat work, that I erase and I don't let anybody see this when I look at the end. But could I turn this into this? Well, notice here I've got these knots in front of the P and a knot in front of the Q. I have to introduce these knots that aren't there. So once again, I want to kind of introduce the knots using the double negation law. So this would be a not P, and to get the knots in front of the Q, I could replace that with not Q. Okay, so I'm just using the double negation law here twice to kind of introduce those those knots that I don't see. Okay. And now, okay, notice that this knot is outside the parentheses. So it looks like, you know, if I can use De Morgan's law on this, I could rewrite it. So remember, so De Morgan's law, I basically take out this negative. Okay, so I'll have a not P there. I've got to change the operation in the middle from an and to an or. And then I take out the negative there as well and just leave what's there. So that's De Morgan. Okay. And that's exactly what I was trying to get it for. So my little kind of working back and meet in the middle. So I know if I apply the implication law to this one, then I'm going to get not. And this is equivalent to P implies not Q. All right, and one more. So we have a not. P implies Q. And we want to show that's logically equivalent to P and not Q. Okay, this one over here doesn't have any implication in it, so let's go ahead and start with the implication law and rewrite this and get rid of the implication. Okay, so we can replace that with not P or Q by the implication law. Okay, and then I've got this negative on the outside of these parentheses, so I can use De Morgan to sort of distribute it through there in a sense. So if I'm going to go not the first thing, I have to change that or into an and then not the second thing. So I've used De Morgan's law there. And I'm really close to what I want, right? But I've got to replace this not P with P. Okay, and that, of course, is double negation. So notice I've just kind of used the same laws over and over again to prove these different logical equivalences. So that's good practice for using them, and we can improve lots of different logical equivalences using the various laws. Okay, so for a little bit of extra practice, you might want to go on your own and try some of these exercises from the book, from the black book, the Chartrand book, and also there are exercises in Zybooks in section 1.4 that you can do as well, and the answers are available for you there, so you can check your work and make sure that you're doing everything correctly.